Welcome to all of you. Today we are going to discuss the topic that is periodic properties. We know elements are arranged in different groups and periods, and they are classified on the basis of their properties. How the properties of the elements changes along the group and period. We will discuss these properties. The properties which changes along the group and periods are called periodic properties. Properties which changes along the group and period is called periodic properties. Before discussing the periodic properties, we have to know some important important characteristic of the elements. By these properties, the other properties changes along the groups and periods. First important properties is that important effect is that is affecting nuclear charge. Affecting nuclear charge, that is, this effective nuclear charge, that is symbol is Z effective or Z star. It is the net positive charge experienced by an electron in a multi-electron atom. That means how much of charge influenced by the nucleus giving attraction toward the outermost electron. Then the outermost electron experienced how much positive charge, that is called effective nuclear charge. Effective nuclear charge. Here nucleus attracts the outermost electron. Then how much force is giving toward the outermost electron, that is called effective nuclear charge. Effective nuclear charge generally written as Z effective. It is equal to Z minus S. What is Z? Z is the denotes the atomic number, that is number of protons, and S is the number of electrons available in between the outermost electron and nucleus. Or we can say it is also called as that shielding constant. It is also called shielding constant, or it is called as number of, that is the density of electron available in between the outermost electron and nucleus. This is called S. So ultimately the Z effective, it depends upon the value of S. If the number of electron in between the outermost electron and nucleus will be more, then the S value will be more. If S value will be more, then automatically Z effective will be less, because the Z is constant, number of protons in the atom is constant. But if the S changes, that is the number of electron in between the outermost electron and nucleus changes, then Z effective changes. What are the application of effective nuclear charge? Effective nuclear charge, first application is more Z effective, less is the size of atom. Is very important. If Z effective is more, then size of atom will be less. For example, lithium to sodium. Lithium to sodium. Here what happens? Lithium is small size and sodium is large size. That means lithium is smaller size, means if you see the Z effective of lithium is more compared to the sodium, because when we move from lithium to sodium, the new electrons added in between the outermost cell and nucleus. These added electron opposes the attraction between the attraction between the nucleus and outermost electron. Due to this attraction, the Z effective will be, due to this attraction, Z effective will be more. But here, due to the inner electron of sodium, the Z effective is less. Due to low Z effective, sodium is larger size. So more will be the ionization energy. That means very important things in, if we will discuss later, that if the Z effective is more, then the attraction toward the outermost electron will be more. So it requires more energy to remove electron from the outermost cell. That is called ionization energy. So when Z effective will be more, then ionization energy will be more. Then when Z effective will be more, size will be less. So these are very important two things regarding the that factors affecting Z effective. So you see the that one figure you see here. This is the nucleus, this is the outermost electron, and this is the inner electron in between the nucleus and outermost. If the number of electron will be more, then the attraction will be less. So if number of electron will be less, then attraction will be more. So ultimately, how much force is giving by the nucleus toward the outermost electron is, that is called Z effective. How much net positive charge experienced by the electron, experienced by the outermost electron, is called effective nuclear charge. Then shielding effect, it is also very important effect in periodic classification. That is, it is also called screening effect. What is this? The shielding effect or screening effect can be defined as the reduction in the effective nuclear charge on the electron cloud due to a difference in attraction force on the electron on the atom. Here is, you see, shielding effect means opposing tendency of the inner electron, opposing tendency of electron, inner electron for the attraction between outermost electron and nucleus. So reduction, when the shielding effect will be more, then the reduction in the effective nuclear charge, automatically the effective nuclear charge will be less, because the inner electron opposes the attraction between the outermost electron and nucleus. This inner electron, this opposing tendency, this obstruction of inner electron or the attraction of nucleus and outermost electron is called shielding effect or screening effect. So when shielding effect will be more, screening effect will be more, means number of electron in between the nucleus and electron is more, then the effective nuclear charge will be less. So this reduction of effective nuclear charge by the inner electron is called shielding effect or screening effect. If number of inner electron will be more, then shielding effect will be more. It is observed, if you see s orbital, p orbital, d and f orbital, the electron in s orbital opposes more compared to p orbital, then d orbital, then f orbital. So shielding effect of s electron is more than p electron, than d electron, than f electron. Here f electron has poorest shielding effect because it depends upon size. F subcell has diffuse structure. Diffuse means it is more scattered. So the shielding effect, the opposing tendency of f electron is less. That's why this is the order of shielding effect: s electron, p electron, d electron and f electron. So more the effect, more will be the size of atom. Is very important. If this tendency, opposing tendency will be more, then attraction will be less. When attraction will be less, then size will be more. Top to bottom, it increases due to addition of new cell. Top to bottom, generally new cells are added, so electron in the new cells in the inner cell opposes the attraction between outermost electron and nucleus. That's why the shielding effect will be, shielding effect generally increases from top to bottom, and from left to right this shielding effect generally decreases. So this is the very important that property, how this shielding effect changes along the group and periods. Then another important effect is that is inert pair effect. The very important thing is inert pair effect. What is inert pair effect? Inert pair effect, you see the term. Inert means stable, pair means two electrons. Then the inert pair effect is the tendency of outermost NH2 electron not to participate in the bond formation due to extra stability. Very important the term. Again I am repeating. It is the tendency of outermost NH2 electron not to participate in the bond formation due to extra stability. This NH2 electron is tightly held by the nucleus. When this effect takes place, the NH2 electron, outermost NH2 electron is tightly held by the nucleus. So the tendency to participate in bond formation is very less. This effect is called inert pair effect. Generally, you see in this structure, you see this is the outermost electron. This is the two outermost electron. Then this is the nucleus. When this outermost electron will be more tightly bonded by the nucleus, then these two electrons will not take part in bond formation, because due to extra stability. When it is tightly attracted, when it is strongly attracted by the nucleus, then its tendency to participate in the bond formation will be less, and this is called inert pair effect. When this inert pair effect observed, when the atom has F electrons, F means F subcell containing electrons. In between the outermost electron and nucleus, if F subcell electron will be available, then F subcell has a low screening effect. Due to low screening effect, the NH2 electron, outermost NH2 electron, will be strongly attracted by the nucleus, will be tightly held by the nucleus, so it will not take part in the bond formation. So that is called inert pair effect. When F subcell will be available, then inert pair effect will be more in compared to P subcell, that is D subcell, P subcell and S subcell. So generally the outermost S electron, that is S has capacity 2, so outermost NH2 electron does not take part in the bond formation. This effect is called inert pair effect, and it is due to the pore shielding effect of F subcell. Already I have told you, when in between the outermost electron and nucleus F subcell will be available, electron of F subcell will be available, then F subcell has very pore shielding effect, so the nucleus will attract a greater force the outermost NH2 electron. That's why NH2 electron will be very less tendency to participate in bond formation. So this effect increases from top to bottom. Generally from top to bottom, this effect increases, because top to bottom, generally when you move from top to bottom, the F subcell starts at the lower, that the bottom atom. When the bottom atom, if you consider the 7th cell, then or 6th cell, then it has F subcell. When F subcell starts, then inert pair effect will be observed. So it increases from top to bottom. What are the application of inert pair effect? Due to inert pair effect, the stability of lower charge, lower oxidation state increases from top to bottom. When you move from top to bottom, the lower charge stability will be more compared to higher charge. For example, that is boron family, boron, aluminum, gallium, indium, thallium, these are boron family, group 13. In group 13, thallium shows inert pair effect. Due to inert pair effect, as the group 13 has 3 electron outermost shell, that 2 electron in S and 1 electron in P, but S2 electron, due to extra stability, due to inert pair effect, does not take part in the bond formation, so only P electron take part. That's why thallium shows only +1 oxidation state, which is more stable compared to thallium trichloride. In group 13, thallium chloride, monochloride is more stable than thallium trichloride, because thallium plus is more stable than thallium +3 due to inert pair effect. Similarly, group 14, if you see, lead +2 is more stable than Pb +4 due to inert pair. When inert pair effect starts, then the stability of lower oxidation state will be more, because the NH2 electron does not take part in bond formation. That's why lower state will be more stable. So thallium +1 is more stable than thallium +3. Pb plus 2 is more stable than Pb plus 4. So these are the very important application of inert effect. Another application also you can say thallium chloride is ionic but thallium trichloride is covalent. Similarly, PbCl2 is ionic, PbCl4 is covalent. This is due to inert effect. Next is regarding atomic radius, that is atomic size. It is the distance between the outermost electron and nucleus. This is called atomic radius. Distance between the nucleus and outermost electron is called atomic radius or atomic size. Then what is ionic radius? It is the same. It is the distance between the outermost electron and nucleus of an ion. Ion means either it is a cation or it is maybe anion. This is, suppose this is an atom. Now this atom contains one electron in outermost shell. This electron is revolving, you see, and two electron in K shell and one electron in outermost shell. When this electron will be removed, when this electron will be removed, then it will be converted to the cation. Loss of electron results formation of cation. When the cation occurs, you see electron is removed from the outermost shell. When electron removed from outermost shell, then nucleus will attract the remaining electron with greater force. That's why size is decreases. This thing remember, when electron will be removing from the atom, then the nucleus attract the remaining electron with greater force. That's why size of the cation decreases. So cation is smaller than an atom. Similarly, if you see this is one atom, if electron will be added to this atom, then it will be formation of anion. So this is the atom where electron is added, electron here added to the atom. When electron added to the atom, then it will form the anion. Then size will be more. When electron added, then the attraction between the outermost electron will be less, because the added electron and the electron remains in between the added electron and nucleus, opposes the attraction. That's why anion is larger size compared to atom. So if you compare the size, this is anion larger size, then atom less, then cation again less. So this is the order of anion is larger than atom, then atom is larger than cation. So largest is anion and smallest is cation. So this is anion, cation and atom and their atomic size comparison. Just you see, this is the addition of electron. When the electron is added, then produce which one? Formation of anion. Then factors affecting size. What are the factors affecting size is very important. You see, generally atoms, if compared to size, there are three types of atomic size generally we observe. What are these atomic size? One is covalent size, that is covalent radius. Another is metallic radius. Another is van der Waals radius. Covalent radius means the bond is covalent bond, and metallic radius means the bond is metallic bond, and van der Waals radius means the bond is van der Waals force. If you see, van der Waals force is the weakest force, it is a very weak force. It is just you see there is a gap, some gap in between the atoms. But in case of metallic, just the two atoms combine to each other. But in case of covalent, the atoms, their cell and subcells are just overlapping each other. Here both atoms overlap each other, just like this. This is just touching, this is the gap, this is overlapping. Now you are maintaining gap. So this is we can say van der Waals force. This is the van der Waals force. If it will be just touching, we can say it is a metallic force. If it is overlapping, that is covalent. So the covalent the bond is more stronger compared to metallic than van der Waals. So as it is very closer, so radius is smallest radius. compared to metallic and van der Waals. As the van der Waals, the two nuclei, the gap is more, so radius is more. Here two nuclei just touching one another, so it is greater size compared to van der Waals. And here these two atoms just overlapping each other, so the distance between two nucleus will be less, so this is the smaller size. So in compared to size, van der Waals radius is greater than metallic radius than covalent radius. Radius means it is the distance between two nucleus. That is, it will be always the distance between two nucleus will be divided by 2. When you divide 2, because in between two nucleus, two radius are there. First radius of the first atom, second radius of the second atom. So in both cases, two radius are there. So what is the actual radius? By 2. So this is the distance between two nucleus by 2. It is the distance between two nucleus by 2. It is the distance between two nucleus by 2. As the distance is very less, so covalent radius is the smallest radius. Then as the distance is more, so van der Waals radius is the largest radius. So this is regarding the types of radii: covalent radii, metallic radii, and that is van der Waals radii. Then greater the shielding effect. If shielding effect means opposing tendency is more, then size will be more. If shielding effect is more, size will be more. Size increases from top to bottom. Size increases from top to bottom due to increasing shielding effect. That's why size increases. We know lanthanides and actinides size decreases along the series. Lanthanides and actinides, these are the two series are placed below the table, and their size generally decreases from left to right. As size decreases from left to right due to poor shielding effect of F subcell. In case of lanthan actinides, F subcells are already available. As F subcell is available, the shielding effect will be less. As shielding effect is less, then automatically attraction is more, so size will be less. That's why lanthanides, actinides shows lanthanide and actinide contraction, the decreasing in size due to poor shielding effect of F subcell. From left to right, their size decreases. Then greater the Z effective, smaller the size. Already we have discussed, if Z effective is more, attraction will be more, then size will be less. That's why size of elements decreases from left to right. From left to right, size decreases due to increasing Z effective. And difference of size is very less among the transition series. If you see the transition series, that the middle series, that their size difference is very less, because these two cuts. First is shielding effect is increasing and nuclear charge also increasing. From left to right, from scandium to zinc, if you consider from scandium to zinc, the atomic radius the nuclear charge is increasing, and the added electron also, that showing the more shielding effect. So shielding effect is increasing from left to right, and nuclear charge are increasing left to right. If both are increasing, but both are in opposite, their property are opposite. Shielding effect increases means size increases. When nuclear charge increases, size decreases. If one is increasing and other is decreasing the size, that's why their size difference between the transition element is very less, or we can say almost the middle elements have similar size due to increase in shielding effect and increase in nuclear charge. That's why transition elements, their size difference is very less along the series. For isoelectronic species, isoelectron means having same electron. For example, Na plus has 10 electron, Mg2 plus has 10 electron, aluminum 3 plus has also 10 electron, but their Z value, number of protons, sodium plus 11, Mg2 plus 12, and aluminum 3 plus 13. As the Z value is more, but number of electrons are same, then the attraction between the nucleus and outermost electron will be more, because as the Z value is more, attraction will be more when the number of electron will be same. Here Na Na plus, Mg2 plus and aluminum 3 plus, their number of protons are increasing from sodium to aluminum, but number of electrons are remain same. That's why attraction is more, Z effective is more in case of aluminum. If you see, aluminum has more Z effective nuclear charge will be more in case of aluminum. That's why aluminum ion is smaller than Mg2 plus. Mg2 plus is smaller than Na2 plus, Na plus. That's why Na plus, Mg2 plus, aluminum 3 plus, their size is decreasing from sodium to aluminum due to increasing Z value and increasing Z effective. That is very important. You compare the size of atoms by taking so many factors: shielding effect, Z effective, then nature of force, whether van der Waals force or metallic force or covalent force. So we can compare the size of atoms along the group and along the period and in the particular block, in particular series. Okay. Then next important thing is valency. We know valency is the number of electron lose or gain or share by the atom during the bond formation. You know there are three types of bond: generally ionic bond, covalent bond, and there is metallic bond. But in case of ionic bond, electron loss and gain take place. One atom losing electron, other atom gaining electron. That's a loss of electron or gain of electron. But a covalent bond is formed due to the sharing of electrons. So when electron will be involved, how many number of electrons involved in the loss or gain or sharing of electrons, sharing by the atoms during the bond formation? That is called valency. Valency of the atom in the group generally remains same. They have same valency, constant valency along the group, because the number of outermost electron is same. Why the valency of the atom in the group, all group elements having same valency? Because their number of valence electrons are same, outermost electrons are same. That's why that valency is same, generally same valency. But from left to right, their valency increases. Why the valency increases? Because the number of valence electron increases. For example, sodium. Sodium, this is the first group, magnesium second group, aluminum 13, that is third group, 13 group, silicon 14 group, phosphorus 15 group, sulfur 16 group, and your halogen 17 groups. If you see from sodium to halogens, sodium produce NF, magnesium produce MgF2, aluminum AlF3, silicon SiF4, and phosphorus PF5, sulfur SF6, iodine IF7. As the valency increases from left to right, there you see the formula changes from, it is monovalent, divalent, trivalent, tetravalent, pentavalent, hexavalent and heptavalent. As the number of valence electron is more, sodium 1 valence electron, magnesium 2 valence electron, aluminum 3 valence electron, silicon 4 valence electron, phosphorus 5, sulfur 6 and iodine 7. As the number of valence electron increases, so the covalence is more. That's all the formation of ionic bond nature will, number of more electron will be gain and lost by the atoms. That's why valence is more. So valency generally increases from left to right, and along the group the valency remaining same. What are the factors regarding the valency? Atom having vacant d orbital. If atom having vacant d orbital, then shows higher valency. For example, fluorine in the halogen family, fluorine cannot show higher valency because it has no vacant orbital. But in halogen, that is iodine, shows higher valency, monovalent, trivalent, pentavalent and heptavalent, IF, IF3, IF5, IF7. But fluorine cannot form Fi3, Fi5, Fi7 because fluorine has no vacant d orbital, so it cannot show higher valency. So that is one important factor. Remember, if atom has vacant orbital, then it can show more valency, more oxidation states. So these are very important factors regarding the valency. Due to inert effect, the valency of the atom become less. So more inert effect, less will be the valency. We know boron family, carbon family, they show, boron family shows +1, the higher, due to inert effect, the bottom atom, the lower atom shows +1 state. And similarly in carbon family, they shows also the bottom, that is lead, shows +2 state. So from when you move from in the p, generally in the p block, when you move from top to bottom, the lower oxidation state is more stable. So due to inert effect, that inert effect generally increases from top to bottom. Due to inert effect, they shows lower valency. So it is the conclusion that when the atom has inert effect, if it is showing the inert effect, if the inert effect is more, then it shows lower valency, lower ion, its lower oxidation state will be more stable compared to higher oxidation state. So more inert effect, lower will be the valency. So for example, thallium shows thallium chloride, which is more stable, or thallium trichloride is unstable. Pb, already we discussed, PbCl2 is more stable compared to PbCl4, because Pb+2 is more stable than Pb+4 due to inert effect. So these are some important factors affecting the valency of the atom. So these are some important periodic properties. In the next class, we will discuss more regarding the periodic properties of the elements. Okay? Thank you all.